Okay, I've been given the thumbs up, so let's get this started. Today, our first speaker is going to be Scot, and Scot, I'll ask you to share your screen and give an overview of your presentation. If you have questions, people, please ask them in the Q&A session, and I'll read them out to Scot.
Okay, good morning. My name is Scott Gould. I'm a professor of physics. I've been a professor of physics for many decades now, as my students remind me. And I'm here to talk about my use of Maple in my classrooms. I've been using Maple for about 20 years, although probably for the last 10 years, I've been trying to use it in every single type of course. Writing from the undergraduate intro physics course all the way up to the most advanced physics course as well. And basically this talk is on my experiences of what has worked for me and what has not worked for me. If you saw my talk, I'm sorry, this should be sufficient. My suggestion is actually just to download the document that I provided and you can get a lot of the details, but I'm happy to answer questions here. I start with basically two religious questions. Again, this is for you if you were an instructor in an undergraduate institution. Okay, my big philosophy here is I want to get people to recognize Maple not as a glorified calculator, but rather as a full enriching educational and documenting presentation environment. Okay. So first of all, the first religious question always comes up is, should be worksheet mode or document mode? The last time, for a long time, there was no way you could use document mode because you couldn't skip from one execution group to another. They at least fixed that in 2021. However, this past semester, when I used it, I let students try either one. Eventually, almost everyone migrated to worksheet mode. They found it much easier because they kept the text in the text boxes, they kept the execution groups in the execution boxes, and they didn't get a situation where sometimes they would write what they assumed were executable math only to discover it wasn't. So that just makes the life easier. If you're starting with Maple and the students have never been exposed to it, start with worksheet mode. That tends to work better. The other religious question, of course, is Maple input versus 2D input. And a lot of the purists will say certainly Maple input is the best way. The problem is the students view the Maple input as coding. And our goal here is to do math. So what I suggest, and again, what students actually come back to Maple, even if they're exposed to MATLAB or Mathematica. Most of my colleagues actually use Mathematica. The students will return back to Maple because it is far more readable to them. Okay, here's one even they did. The students were able to show me that things that I used to worry about, like add versus sum, Maple, particularly the 2D input, has gotten smarter and smarter, and these types of things you don't need to do. 2D input is just basically the best choice. And being able to write the function as f of x, not f as a x goes to an operator. So the things that certainly they love to do is things like subscripts. I show them the subscripts, I worry about them, but they love to be creative. This sells. Being able to put vector signs over your variables, that sells. Obviously, symbolic calculation sells. Clearly getting down to a nearly single command solve function. And there is a single command solve function. It's buried in PD tools. But I would like to see at some point, and of course, this is directed towards the people of Maple, can we get down to a single so that we don't have to have this problem of, oh, that's right, I shouldn't have used solved, I should have used fsolved, I shouldn't have used dsolved, I should have used solved for different problems. Okay, and of course, they do like the documentation capabilities. I'd like to point out, this is a beautiful worksheet that I can't do in any other program that I've ever seen, where literally the vector P, and it's got a vector sign over it, and the fact it's got a dot product, or I'd say the dot notation to show that it is a derivative with respect to time. Maple beautifully reads this out as a series of vectors, does the operations on them, and actually can solve these things quickly, okay, and get solutions, Okay, nicely and algebraic. And now I actually can do it also for numerical solutions. This has been very, very a big sell for the students. Okay. However, the single biggest complaint by the students is creating functions from expressions, because it starts with using the single least intuitive named function, I would say, in Maple, which is unapply. I don't know why it's unapply, but it is unapply. If there was something like make function or create function or something like that, that would be some more less unintuitive than unapply. Because again, these students are going to work on your projects, but they're eventually going to go off and do other stuff, and they're going to come back and they're not going to remember certain non-intuitively named functions like this. But otherwise, the other biggest complaint they have, of course, is really simplify. And this led to an interesting discussion in the networking group this morning, which I strongly suggest you go to. But this is a necessary evil, and you just simply have to remind the students, to whatever solution they get, they should try to simplify and give the solution, give Maple some help in the assumptions. There are some issues, of course, is the temporal versus the spatial execution. I have not used Maple Flow, but I think that may be the future for this, and this entire talk will be revamped using Maple Flow. All right. Things you can do to really get students to buy in is to do something in Maple that they have spent hours and hours on, such as doing antiderivatives and showing them that Maple will do it in a few lines. And of course, this morning we saw that was true with Maple Learn. This leads to the greatest collective groan I've ever heard in any class, is when they realize that all those hours they spent on this calculation could have been done quickly in Maple, and they saw the steps. Okay. I also did this with a colleague. A colleague basically did a problem where she said, I want to solve this problem. Here is a minimum. I'm going to start my ball essentially at this location, and I want to watch its motion around this minimum. And she had the calculations done using small perturbation about the equilibrium point. This is unnecessary. A lot of these skill sets, certainly if you're doing applied math, is necessary, since you can do the whole thing in basically 2 lines, or really with a desolve numeric. Okay, so proving to your colleagues that Maple can solve problems faster and more readably than having them do it themselves makes a big difference. Okay, certainly 2D plots are beautiful. 3D plots are beautiful. Okay. All these things, putting colors in. Students love colors. I mean, who doesn't like XKCD booger color? I mean, that's the most beautiful color there's got to be. Okay. Indeed, if you want to make your life easier, I found that getting all problems to end in a plot really helps me decide whether students know what they're doing or what they don't. Okay. 3D animation certainly makes a huge difference. Exploring systems, using the explore function, they love to do apps. Okay, they like to use the explore app to basically put the sliders up and make their own sort of Maple app. All right, and they can also reproduce physical systems. And for me as a physicist, this is good. This is the image that one sees when one shines light through 2 slits, what it appears actually on the wall on the other side of the slits. And so being able to control the wavelength of light going through, control the spacing, etc., they get to reproduce the truth. Okay. Here is the last thing that I would say that really students have in my class have gone to, is the ability to use the parameter option in numeric. So here is a situation where this is a classic from physics, is known as Atwood's machine. However, what we've done is we've added a swing. So we're going to basically pull this ball back and allow it to swing. And as a consequence, there is tension in the rope. The functions look exactly what we do in the book, but adding the parameters option to the desolve and then outputting as list procedures, that's another very, very useful thing, instead of using ODE's plot, because again, that's another function they have to remember. you end up being able to explore the whole function beautifully and watch the trajectory of this blue ball as it goes back and forth. And so the best way I have found to teach Maple is to get the students to build their own apps to build. So everything that you have seen in here has come from a project the students have designed on their own, except for I think this last one I actually had to write, draw my own. That's about it. Certainly there's a whole bunch of things that frustrates. I will leave this to the people who write Maple, who design Maple, and I'm happy to talk about to them. One of the big things I will mention is the context panel just does not sell. It does not have a sufficient amount of depth to it. It leads to frustrations. Things like changing the plot widths are too cumbersome. So students generally in the end don't use the context panel. Okay. Oh, my other personal complaint, please work on improving the PDF generator. The rest of this talk, and again, go online, is to find out, and I can tell you the protocol in which I teach Maple, and if you go through that process, you can see what tends to work for me. All right, and that's my spiel.
Thank you, Scott. So we've run out of time for questions. Hopefully at the end of this, there will be time. I know I found the what frustrates part very interesting as the product manager in charge of, teaching and learning and academics. So I do have a few questions for you. If there's time, we'll come back and we'll get a chance to bring that up.
Thank you.
But now I'd like to invite Phil Yasskin. If you would please come and kind of give an overview of your presentation.
Hello, let me share screen. There we go. Okay, so this is the calculus book I'm writing. The main contents looks like this. You can get Calc 1, Calc 2, Calc 3. As I go through the textbook chapters, please text which chapter you'd like me to show in more detail, and I'll be happy to do that. There is a website here, which is available. Can I put this in the chat and everyone can see it? I presume so, but that is the website.
Yeah, if you put it in the chat, everybody will get it, Phil.
If I put it in the chat?
Yes.
Okay. Copy.
Just make sure you select everyone.
Chat. Where is the chat now? I lost my chat. Anyway, maybe you can put it in. I don't see where the chat is when I'm on full screen. Chat. Paste. Okay. There we go. Back to sharing screen. Okay. So Calc 1 is the least finished of the chapters, and the pre-cal is not yet finished. The trig is ready and the vectors are ready. And you'll notice this is the sample column chapter version. And so it says available as samples. Limits. We've got intuitive limits, computing limits, precise limits, applications, derivatives. We have tangent lines, derivative rules, linear approximation, chain rule, inverse, higher. Remember, please text which chapters you'd like me to discuss in more detail. Limits includes L'Hopital's rule and Newton's method, related rates, lots of word problems that of course the students hate. Again, in max-min, word problems. Properties of graphs is another type of application. And integrals is basically a repeat of the first couple chapters in Calc 2. Let me switch over to the full version here. So Calc 2, we've got all the techniques, all the applications. In particular, volume has lots of animations, So does arc length and surface area. Differential equations is an introduction to differential equation, having separable and linear and slope fields, and applications, including mixing problems. Sequences and series, standard treatment, Calc 3. Part of it is coordinate systems, vectors, dot products, cross products, properties of curves. You'll notice line integrals is here about 1/4 of the way into the book, whereas something like Stewart leaves line integrals to in the middle of learning about the theorems. And that's hard for the students because it's intermixed with theorems. They need to learn it separately. Derivatives, tangent planes, chain rule, directional derivatives, max min again in higher variables, divergence and curls, including vector potentials, not just scalar potentials. Things can be skipped by an instructor if they desire. Iterated integrals, get them computing before I go into the details of what it needs, using rectangular coordinates in 2 and 3 dimensions, along with their applications. Curvilinear coordinates, polar, cylindrical. Oops, I seem to have gone over to the actual chapter. And then we have curvilinear coordinates, which includes general coordinate systems and Jacobians, and then moving to parametric surfaces. Again, get this done so students have a chance to understand surface integrals in their own right, primarily parametrically, before they start talking about the theorems, fundamental theorem of calculus, Green's, Gauss, and Stokes are done there. Okay, so moderator, do we have any requests for a particular chapter?
There have been no requests for a particular chapter.
Okay,
There have
so
been.
I will go on and pick a chapter. Volumes
Okay.
of
We have
Revolution.
two more minutes.
Okay, volumes by slicing. You can see that there are animations of the slicing. I'll go over to the exercise page, and you can see that, oops, I gotta get rid of my Zoom windows. Here is volumes of Revolution, which give discs, lots of problems. The students get to do the problem, read a hint, check their answer against the answer. If they can't figure it out, they can go to the solutions and see lots of animations, most of which have been made in Maple. Any other questions yet? Washers?
There is a question. So one question is, for rational trig integration, sine t over 1 cos t, do you cover the tan half angle substitution?
Tangent half angle. No. That's not in there, but it is something I could add if a particular faculty member at a particular institution wants it. So this is for trig integrals, is that right?
Yeah, the question was rational trig integrations. Do you cover the tan half angle substitution?
No, it's not in here. It could be added, but it's not currently in there.
We have another question, and when going to the website, the security certificate states it has expired, which gives a warning.
Yes, I have to check into why that happens. But it should, you can just go past it, just do advanced and say go anyway. I can't think of anything that would be in there that's dangerous. You're just viewing web pages.
And then, oh, there's another question. Okay. And one last question that I got, in fact, I got from one of our colleague is in your talk, you mentioned the difference. You had said there was a pilot project for students using your textbook versus the Stewart one. Can you talk a little bit more about how that pilot project has been going and what students have noticed?
Students like the interactivity. They like the answers and solutions on essentially everything. When you try to do something, it has lots of pictures and links, and they get to do a problem. It lets them read an answer separately from reading a full solution. I've been teaching it now for about 3 years, starting with Calc 3. This was the first semester I taught Calc 1. I've had 3 other A&M faculty teaching one course each, and they've been positive about it. The course evaluations from the students have said they like the graphics in particular, most of which is done using Maple.
Great. Thank you very much for your presentation, Phil. And then again, if there's time afterwards, if there are other questions, then we'll have time for that, or for any of the presenters. At this point, we'll move on, and Matteo, if you could please share your presentation and give us an overview of your talk.
Yes, thank you very much. So my name is Matteo Sacchet. I am a postdoctoral researcher from the University of Turin in Italy, and I would like to tell you something about some tips for successful creation of contextualized problems for secondary school students with Maple in particular, because the students at all levels and in all countries of the world need to practice mathematical problem solving to develop competencies that they will apply in their real life. My experience is based on the digital math training project, whose aim is helping secondary school students to develop and strengthen mathematical and computer science skills through problem-solving activities. These students had training in labs in their school with the whole class. But then for the project, we selected 3 of the most skilled and motivated students to participate to an online training in which was more advanced. They have to solve a problem every 10 days and submit their solution to the tutors. In the meanwhile, students were accompanied with synchronous tutoring in the use of Maple and also in the problem-solving approach. So the main question that is behind this project is how to set up a problem to be proposed to the students. It is important to carefully plan and present the activity to the students. The text of the problem should be clear with the storytelling to enter into the setting of the problem, not be too theoretical, or maybe it could inspect the specific aspects of the related theory. And also making use of the computing environment. In order to prepare these problems, we follow precise design principles, both in the practice and in the use of Maple. And this principle, of course, can be adapted to different situations. And I will try to present some of the useful tips from our experience. One of the starting point is the brainstorming, because the teacher has to reach the goal it said make students reach the goal. This is the objective of the activity of the problem-solving approach. So, for example, just in having a look at where is mathematics, what can I propose to students? So, math is more or less everywhere. It's the language of the universe. So, when we were thinking about the problems activities, we were thinking about the basic areas in mathematics, like quantities, space and shape, changes and relations, and uncertainty. For example, the animation below shows like a circle around an ellipse, which looks like in the real life a person practicing hula hoop, for example. And the second tip is about the design. When the teacher has to design the activity, he has to think about all the details. Who is the target? What are the prerequisites? Is the activity group or individual one? Then, of course, a little bit of storytelling can engage the way students approach the activity. The scenario of the activity, even if it is composed of very short sentences, but can make students absorb the message from the start to the finish. So do not forget also to fully describe, so a teacher, to fully describe the activity from the mathematical point of view. For example, new or unclear concept to the students can be shortly explained in the text of the problem. And teacher can guide students with hints, but also let them try their own way to solve the problem. So this could be also, it was also for us a surprise when we were looking at the student solution, which was left open, say, the way to solve the problem. Also, the relevance of the problem is very important because the subject of the activity was a mathematical concept. So, and the mathematical concept it is usually surely used in a real context because this is how mathematics was born. So this context of the mathematical entity is the most suitable to as a background for the activity. Another useful hint is the division into multiple requests. This is called segmentation. So it is better if the problem is presented into step-by-step process, a step-by-step question, rather than a continuous entity. Otherwise, it is easy for the student to get stuck. So we usually start from simple requests, so everyone can do them more or less, going to the most difficult ones. We also try to push the students to their limit of their knowledge to explore new scenarios. We do it in different ways, and to reward also with the intellectual engagement and challenge, and also in checking their ideas. I just show little examples in this presentation. We made also students build the components in order to compute the distance between two cities, inserting just the coordinates, geographical coordinates. Another important part, of course, is made by technology. Most of the mathematics at school, secondary school, is done with paper and pen. But normally, every person uses, even students using technology to manage problems, to cheat on mathematical activities. So the use of the calculator is very important, and also I try to give you some hints about how to use Maple in this process. There are two principal ways that we adopted. So one way is using the startup code in order to create procedures that were easier for students. So in not focusing too much on the for example, for the conversion of some numbers into different formats, we prepare some pre-built procedures that students just has to use as they were, using the startup code in Maple. And another Maple tip, let me say, is the generalization, the exploration of the concepts using interacting components to really generalize the problem with different data and obtain results according to specific models. This lets students also get used to provide the requested information to any user. So just moving the slider or changing the variables in the text area. In order to face the same problem, the same situation, but into a different context. Here is just a little summary of there's also my email if you want to contact me, and I made a little overview of the many components and animations. We spoke about animation even before Scot or Laurent also. So we use them, they are very important. This is also a little summary of the 10 tips that we adopted for creating contextualized problems for secondary school students.
Thank you so much, Matteo. This was fascinating. I really enjoyed listening to all the tips and kind of hearing the success that you've had in the classroom. One question that I did have was, could you talk a little bit in the classroom environment? I'm sure there's students at different levels. You know, some are the exceptional math students and some students might be struggling. Could you offer some tips or strategies to kind of balance it so that the kids that are struggling can continue to follow along? Like, how do you manage that?
Yeah, okay. Actually, this kind of project was not intended for, let's say, a larger audience, let me say. But we, say, before the training part, we went into the classes, so into the labs with the students. And so there were the physical presence of the tutors of the project with the students. And so we tried to involve every kind of students, so the weak ones and the strong ones, all together in the discussion. In that situations, okay, we use Maple in order to show the capability of the environment, which maybe can make math sounds like easier than the one done by paper and pen. And also, say, with an approach which is suitable for students, and also involving the strong students in helping their classmates.
Thank you so much. I appreciate this. Again, to the audience, if there are further questions, if there's a little bit of time, we can hopefully do it. And then I see Scott also mentioned there are the networking sessions. So if we don't have time in the presentation, I'd encourage all of the participants of this session to attend a networking session, and it's a good way for you to ask questions. At this point, we'll move along. And Eugenio, if you would please present an overview of your talk.
Okay, thank you. Can you see the Maple worksheet?
Yes, we can see it.
Okay, thank you. Well, the title of the talk is the Maple-based introductory visual guide to Gröbner bases. And there's an antecedent of this work. This work is done by myself and my father, is also a mathematician, that in 1975 wrote a monograph entitled something like Geometric Interpretation of Ideal Theory. That was an introduction with many plots and many drawings to classic books like Zariski Samuel. I think there's still a place for something like a visual guide to Gröbner bases. I teach a PhD course to engineers. In fact, it's a mathematical engineering course. And I need to use Maple, I need to use Gröbner bases for exact solving of nonlinear systems, and I don't have time to give all the theory behind. So what I present to them is something close to this that I show here, that is an elementary introduction to ideal theory, to commutative algebra and Gröbner theory, Gröbner basis. Well, initially, I introduce what a linear equation and a zero set of an equation is, illustrating it with some plots in the 2D and 3D cases. What is a linear system? What is graphical interpretation? And what Gröbner basis returns in such case. Of course, you don't need Gröbner basis to solve linear systems, but it's an introduction to what is done later with a nonlinear system. What it does is to return the simplest description of the solution, in this case, lines parallel to the coordinate axis. And if the system is given another way, it returns the same. Of course, there can be systems with no solution. It's very important to realize, and then the Gröbner basis will be 1. When there's an infinite number of solutions, that the Gröbner basis describe it. And in the 3D case, we'll have planes instead of lines, and the intersection of those planes will give the solution of the system. And the Gröbner basis will describe the simplest way. In this case, the planes are parallel to the coordinate planes. The locus, the theory locus can be of a high dimension, for instance, a line. And again, the description is the simplest possible with one vertical plane. If there are cases with no solution, and in those cases, the Gröbner basis is 1. And in the algebraic case, we have a similar situation. The difference is that now we have curves instead of lines in the 2D case, surfaces in the 3D case, well, hypersurfaces in the n-dimensional case, and a very serious difference is that now there can be separate components of the zero locus of a point. Like here, when this equation is the union of two non-intersecting loci. When we consider systems, it's the same idea as in the linear systems that the students know from the previous studies. Again, it's the intersection of different curves instead of lines. In the 2D case, the Gröbner basis is the simplest description. And well, if there are more than one component, for instance, here the solution is a couple of points, the description again is simplest as possible. If there are no solution, then 1 is the Gröbner basis. And we must be careful with the difference between what we plot and what we do in the background. Gröbner basis work in C, closed algebraic field. So for instance, in cases like this, although we only see 1 point, there are really 3 points that are the solutions to what the Gröbner basis returns, or what you could do with you solve it in another way. Of course, different systems can lead to the same Gröbner basis, like here the intersection of this circle, this parabola, and this cubic. However you give it, you obtain the same if the order for the monomials or for the variables is the same. In the 3D case, it's more complex, but again, we have surfaces instead of planes. And the description, for instance, here, the intersection is a point, the solution is a point, so it's returned as an intersection of planes. And it can be a curve. And again, the curve is returned in a simpler way. There can be more than one component. For instance, here there's a point here in the foreground and one in the background. And there can be cases with no solutions, like here, to stay at the same time in this cylinder and in these two planes. The Gröbner basis is one. You have to separate, to be aware of the difference between what you plot in R3 in this case and what you are doing in C3. And something curious that is strange for people unaware is that this doesn't work as a vectorial space, that the bases all have the same number of elements. If you change the order for the monomials of the order for the variables, you can have different number of elements in the Gröbner basis. In this case, this has 2 polynomials, and with a different order, you have 4 polynomials for the same set of generators. And finally, the main property of Gröbner basis is that they completely generate the, they completely identify the system from this point of view, the ideal from a more formal point of view. For instance, here, if we give here a circumference as an intersection of an elliptic paraboloid and a plane, and we give it in other ways, like here, intersection of 3 surfaces, at the end, what we get is always the same description. If we don't change the order for the monomials of the variables, in this case is the intersection of a horizontal plane and a vertical cylinder. Which are the applications? I think there are applications everywhere. Whenever you can translate your engineering, physical, mathematical problem into a set of algebraic equations, you can approach it with this technique. An example is to check if a curve is contained in a surface. Other examples are to check if a graph is decolorable, this is due to Trager. And there are open fields like automatic theorem improving in geometry, moving from the construction in the dynamic geometry system to this set of equations, and then to attack it, to try to solve it. Knowledge extraction in knowledge-based systems, etc. So I think it is very useful, and it can be used like many non-mathematicians use with the statistical packages, to have the main ideas, the critical ideas, and to use it, not just having to move to numerical methods. But you have to understand at least the idea of what you're doing, and I think a collection like this can help these non-mathematicians. Thank you very much.
Thank you so much for your talk. Just one comment from myself and a colleague. When I studied my engineering, I never learned about Gröbner basis, and I found this talk just extremely useful. I really found it interesting, and it taught me a lot about a topic I knew very little about. So thank you so much for that. I really appreciated it. There is one chat in the, or there's one question in the Q&A, and it's, I really enjoyed these graphical interpretations of Gröbner bases. Is it possible to get a copy of the Maple worksheet used in your talk? It was not available to download from the conference website.
Okay, I was working in it until the last minute. You can send me an email. This is my email, and I will send it back to you. Or I can send it to you, Karishma, and you can allocate it in the webpage.
Either way works. We'll make sure that participants.
Okay, I can send it to you. No problem. And the paper will be based on this worksheet.
Perfect. Another
Thank
comment
you
that
very
I
much.
see
Yes.
in the Q&A is it's more of a suggestion. Somebody recommends using style equals patch contour, and they say it gives a much better 3D plot. So that's something for you to try out.
Okay, thank you. Thank you. I'll try.
And then one last comment that I also got is to kind of, people wanted to know which class or which level of students you presented this content to.
Okay, it's a PhD course for non-mathematicians. It's an mathematical engineering course at my university, is the main university in Madrid, that offers this course together with the Polytechnic University of Madrid. Then I have normally I have between 6 and 8 students. They normally have a master in electrical or mechanical engineering, physics or mathematics. And my idea is to show how mathematics, in particular computer algebra systems, can be useful in their work. So I present different applications, mainly in transportation engineering and railways, for instance, in decision-making interlocking systems, in airports, also some typical mathematical problems that have a connection with their work. So to try to show that, let's say, mathematical is not only what they studied in the first year in university in calculus and algebra 1, but they can be much more useful, and there are more methods apart from numerical methods. I mean, Gröbner basis can't face very, very big problems, but for instance, I work in artificial intelligence applications with rule-based expert systems with around 100 rules, and we have no problems with extracting knowledge. I mean, not all problems can be treated, but you can treat problems of a good size. But at least they must be aware that these things happen. If you can't face them, you have to try other tools. But this is not very well known outside the commutative algebra world, and it's useful in many different applications.
Well, thank you so much. I found this very informative. And to all of the panelists, we have a few more minutes for questions. Scott, there is a question for you in the Q&A, so if you'll be able to kind of come back online, I'll read that question to you. So the question is for regarding the context panel, what aspects or functionality do you like, and what else would you like what else would you like improved?
Okay, boy, that's going to be a long answer. I love the palettes. I use the palettes all the time. The students love the palettes. They can see it. It's visualized. And in fact, things like, can we do desolve or solve through the palettes? If I literally just drag a little solve icon over onto my function or onto my equation and solve it there, that would be even more useful. But in terms of the context panels, frequently we get started, we can do a few things, and then almost very quickly we run into limitations. I'm going to share my screen. I'll give you a quick example. Okay. So here I basically put in sine of x, and then I asked it to plot it. So I'm clicking on the plot, okay, and that looks beautiful. It's actually larger than I wanted to use, but that's okay. We can drag it, and that all looks good. We can make it smaller. So I want to change I actually don't want to plot it from -2 pi to pi. I want to plot it from somewhere to other. So I figured, oh, I'll go under axes. And I'll go under, well, there's nothing about the edge points. Okay, maybe it's under properties. Oh, I found it under properties. So the range was from here to here. So I want to really plot it from -10 to 10. And I go, okay. And it worked that time. But interestingly enough, if I type plot, x times sine of x, because I just did this 2 seconds ago. Oh, now it's making it smaller. Okay, again, I use, let's see, I want to click on this. I want to use axes. I want to use properties. I go from -10 to 10, and that's what I get. And it didn't plot it from -10 to 10. And so these types of issues, move you over here so you're not seeing the side of my head. These types of issues come up repeatedly. So, and even if you use some of these things, and one of the things that students really like to do is they love the triple exclamation point. And frequently they write stuff out and then the triple exclamation point, and when they redo it, doesn't produce what they want it to produce. Okay, or they lose the information. That's why I tend to go back to, we'll write a little bit of code and not use the, you know, as you see, we've lost the range that I wanted, and the context panel just ends up being not that useful. I can go on to other examples that have come up with the students, and we just simply migrate back. So that's a start.
Thank you for that, and thank you for showing it. And I think my question, again, as product manager, I'm always curious. Firstly, thank you for being so gentle in providing feedback. You know, I think a lot of developers put hard work in this, and we can be a little sensitive about our baby. So I appreciate you sharing feedback and improvements in a very gentle way. And my question is to all of the panelists, now that we have a few minutes, is, you know, what is the #1 thing that you would like to see improved in Maple? So if you had your wish list and there was only one, what would that be? And I'll give you only 3 minutes to think about that, because then we have to wrap up. Matteo, go ahead. I'm going to put you.
I say it's a very tricky question because there are many things that I would like to see. So, but also that's one thing that I say to myself. Many things that I have to explore because I have to know a little bit more all the Maple suite with Maple Learn and so on. I use many of the things, but I think I do not use everything because Maple is very, very large. So one thing that I say to myself, I have to discover more.
Okay. So we need to do a better job in making sure that you kind of know everything that Maple Learn, all of our products have.
I'm trying to do it in the conference, but also, sometimes a little reminder is very useful.
Good, thank you.
I think the answer from the student standpoint would be improved help section. I teach both this and MATLAB, and the students definitely find the help in MATLAB, even though they despise the language. They groan when I have to say, now we have to do this in MATLAB. They would like to see something more akin to the examples that you see in the layout that you see in MATLAB, and also the suggestions. I noticed one thing that Maple is doing is it's providing better suggestions as to what to make the fixes, but there still are a number of errors that get returned for which I have to interpret the ones. For example, the classic one of doing a desolve numerically where not all the parameters have been defined. That's my #1 suggestion.
And perfect. 1 more minute left. Anything from Eugenio, Phil, any other comments? Your wish list, the one thing you'd like to see improved?
I'd like to see better output from plots. We can export as a GIF, but we can't export as an MP4. We don't have control over things like the several things in the plots that I just do not feel that there's enough control over how they come out. Okay.
Great, thank you. I have now been told that we need to wrap up. Eugenio, I'd love to hear what you would have to say. Maybe we can meet in one of the networking sessions.
Okay, yes, about the evolution of Maple, I was using Maple, I think in Maple 5.4 or 5.3 or 5.2, and it's growing and growing more and more. And I wonder if it would be interesting to have a kind of Maple Lite many people still remember derive and the possibilities. And I'm not sure if there's a place, for instance, in secondary education for a reduced version of Maple. I know what Laurent has been showing us of this Maple Learn and all the possibilities. But on the other hand, I even have a paper about how derive is still remembered, and people are still in 2021 writing articles about derive. So I think something like a Maple Light reduced version could be interesting.
Well, let's continue that discussion in one of the networking sessions. So again, to all of the panelists, all the attendees, thank you so much for coming to this. And thank you for taking the time to put these together. I found all of the sessions very, very informative. Thank you so much.
Thank you very much.
Thank you for having us.
Bye.